Hi guys, welcome back to my channel. So today we're going to be talking about expanding and condensing logarithms, and we're going to also cover the change of base formula. So let's take a look at our three basic rules. First off, we have the product rule. So for the product rule, we have in the condensed form, that's where the name is coming from, we have in the condensed form a product of m times n. And when you expand it, it becomes a sum. So still the same base, log base b of m plus log base b of n. Next, there's the quotient rule. So in the condensed form, you'll see that there is a quotient, m over n. And then in the expanded, instead of having a sum, there is a difference. So log base b of m minus log base b of n. And then the last rule is the power rule. So this is basically a repeated product rule. If you have m times itself n times, you can view it as basically doing the product rule n times, so you get a total of n log base b of m terms. So let's again look at the name compared to where it comes from. So the product rule comes from the product in the condensed form. The quotient comes from the quotient in the condensed form, and the power comes from the power. One thing to note about the power rule is that everything inside the argument has to be raised to the power. Okay, so we are going to have to be careful if some things are raised to power, some things are not. It's not just it's not as immediate as some other things. So let's go into our last rule, which is the change of base formula. So the change of base formula isn't really helpful for condensing or expanding per se, but it's the rule that's going to allow us to change any logarithm in a base that would be less desirable, say 2 or 3. The bases that are less desirable tend to be bases that aren't particularly special, so we tend to prefer bases like e and 10 over just other arbitrary bases. So frequently you'll be converting to base e, and how that goes is you start off with the base you had and you think about the base you want. So the formula that does it is you do log whatever base you are wanting to change to, and then of the original argument divided by the log of that same base that you're trying to change to of the old base. Okay, so those are our rules that are at play. And you'll notice there aren't any other rules. I'm not leaving any out. So there's no rule that's going to help us with if we have a sum inside the condensed form. We only have product, quotient, and power. Okay, so let's take a look at some practice problems here. So expanding completely. How I like to do this is kind of a very global approach. I can kind of just look at this and break down some properties. So when I'm expanding, the first thing that I'll do is I'll isolate what is my numerator, what is my denominator. So the terms in the denominator are going to go with the negatives, and the terms in the numerator are going to go with the positive log terms. So let's separately circle every single term. Okay, so in the numerator, the term that I have is there's just one term, root z. In the denominator, I have two terms, x and y. So I know that there's going to be 3 total log terms, and it looks like 2 of them are going to be negative. What goes in the negative ones is x and y, and what goes in the positive one is square root of z for a first step. But notice, I see a power. This is like having ln of z to the 1/2, and everything inside that argument is raised to the power of 1/2. So I can use my power rule, bring that outside, and that's 1/2 ln z minus ln x minus ln y. And that's truly as far as we can go. So when someone says expand completely, they mean using those logarithm rules, break it apart as much as possible. This is going to be particularly helpful for classes such as Calc 2, because you'll need to be integrating things, and it turns out it's actually much easier to integrate these logarithms when they're fully expanded. Okay, so let's take a look at our next example. Circling all our terms in the numerator, I have a 9, I have x minus 5 to the 5th, I have y plus 3. Notice these are terms in the product, not terms in a sum or difference. In the bottom, I have y squared, y minus 2, y plus 4. Okay, so it looks like I'm going to have a total of 6 log terms, and the first 3 will be positive, so log base 3 of 9 plus log base 3 of x minus 5 to the 5th plus log base 3 of y plus 3. And then on the bottom we have minus log base 3 y squared minus log base 3 y minus 2 minus log base 3 y plus 4. Okay, and notice this is not a fraction, so this is one long sum. It's just I kind of ran out of room, so let me write in the next line. We'll write it as one line where there's more space. And let's simplify as we go along. So the first term, log base 3 of 9, we can simplify that. That's asking the power, that's asking what power do you have to raise base 3 to get 9, so that would be 2. And then we have plus, and it looks like the argument has been raised to the power of 5, so we can use the power rule to bring that 5 out. And then we have plus log base 3 y plus 3, and then giving myself a little bit more room here, minus 2 times log base 3 of y minus log base 3 of y minus 2 minus log base 3 of y plus 4. And checking that all the powers have been handled. Yes, this power was handled, the 5 was handled, the 2 was handled. Perfect. And looking at what we have left, this is truly as simplified as we can get. So there's nothing that's going to enable us to get rid of the sums and differences inside logs. Those have to stay. There's just no log rule that simplifies those down any further. Okay, so moving on, we're going to go in the next direction. Let's go, instead of expanding, let's condense these logarithms completely. So the first step, I pretty much do the reverse of the process of expanding. So the first step I'll do is I'll bring the powers inside. And I just bring the positive part of the power. Everyone does this a little bit differently, so it's okay if your way is a little bit different of seeing it. As long as we're getting to the same answer, the way you're doing it's fine. Okay, so we have ln x squared minus ln y cubed plus ln z to the 4th. Now we're going to try and put this into one logarithm, and I know I'm going to have a ratio because I see both positive terms and negative terms. So let's underline what is going to go in the numerator and what's going to go in the denominator. So it looks like positive, the ln x squared term is positive, and the ln of z to the 4th is positive, versus the ln y cubed is negative. So when I write my fraction, I'm going to have in the numerator x squared, z to the 4th, and then in the denominator goes the y cubed. And then I notice my fraction cannot be reduced any further, so that's our answer. Cool. Okay, so let's take a look at this next one. We got a little challenge mode here. So check out the bases. We've got 2 and we've got a half. And if we scroll up and look at our log rules, notice that the pattern for condensing is you need to have the same base. So I cannot immediately apply any of these rules, product, quotient, or power, really. At this point, I have to try and first change the base. Okay, now you might be wondering, why would we want to do this at this point? Well, just like with integrating, you want to have expanded logarithms. When you're solving log equations, you typically want to have condensed logarithms in the same base. So I wouldn't want to solve an equation that involved this sum without first changing the base to 2. So I'm going to change this log base a half of x minus 1. Remember, the pattern is you do log base of what you want, so I want 2. Log base 2 on top and bottom. And then you do log base 2 of what was the original argument over what was the old base. So log base 2 of a half. Now we need to simplify that. Log base 2 of a half. That's asking what power do you raise the 2 to get a 1/2, and the answer would be -1. So it looks like this simplifies as log base 2 of x minus log base 2 of x minus 1. And now I see that I have one positive term, one negative term. So when I write the formula for my condensed logarithm, I'm going to have x in the numerator and x minus 1 in the denominator. And I can't reduce that fraction any further. So there she is. Okay, one note before we finish this video for today, and that note is when you're unsure about how to simplify something, it is better to not simplify it, especially in an exam setting. So at home, you can obviously just look up whether what you're simplifying is valid, or you can take your time and check it carefully. But when you're in a timed situation, such as an exam, this is very much my philosophy. Some teachers may tell you something different, but personally, I'd rather see someone work with something that's unsimplified but correct than try and simplify using false rules of mathematics and end up with something that's just not equivalent to what they're working with and get wrong answers from that point in the problem forward. So frequently in calculus, you're going to see problems that build, and you'll need to take answers that you get and work with them further. So that's where it gets a little dangerous simplifying when you just don't know how. So I'll just leave you guys with a note. For me, please don't simplify unless you're 100% confident that that's how it simplifies. Otherwise, leave it as is. Hopefully this video was helpful, and tune in next time and we'll see how to solve some exponential and logarithmic equations.